Welcome to ICX 200 Module 2 on Advanced Layer 2 Features. In this module, we want everyone to be able to understand and deploy link aggregation group advanced or optional configuration parameters, describe and configure the protected port features on the ICX portfolio, configure VLAN and VE interfaces to route between VLANs on ICX devices, describe and configure aggregated or Q&Q on aggregated VLANs or Q&Q on the ICX portfolio, understand Q&Q BPDU tunneling. So sometimes it's not necessary to only send through data frames through a Q&Q environment. Sometimes you may need to send through control frames. Those could be BPDUs for spanning tree, rapid spanning tree, or multiple spanning tree, or they could be link layer discovery protocol units, or they could be something like LACP to use. So there's a few different scenarios where you want to tunnel control frames through a Q&Q infrastructure. So we'll see how that's done on the ICX portfolio. I want everyone to be able to describe and deploy advanced features with spanning tree, rapid spanning tree. Also see how to implement multiple spanning tree protocol on the ICX portfolio. And we'll do a brief introduction to the concept of VXLANs. So we'll go ahead and start our discussions in this module with optional configuration parameters and some additional discussions around link aggregation groups. So as a quick review, a link aggregation group is a set of ports that you've basically turned into one logical link between two peering devices. So always keep in mind when you're in a multi-vendor environment or when you're doing lags towards edge devices inside your network that different devices, different products from other manufacturers will have different requirements for link aggregation groups. That can include the number of links that could operate in a lag together. It could be specific port boundaries. So always check what's supported on both sides of that overall connection. So for example, if you have a stack of ICX 7150s and you're connecting that to a stack of 7250s or higher within your environment, the 7150 portfolio has a maximum of 8 ports in a link aggregation group. 7250s and higher have a maximum of 16. So you would not be able to create a 12-port lag or a 16-port lag from a stack of 7150s to a stack of 7250s because you have to follow that more specific restriction that is on the 7150 family. Again, this especially gets true when you deal with multi-vendor environments. So, for example, on ICXs, we don't have any kind of port boundaries. Many vendors will use different forwarding ASICs for different sets of ports on their device. So they might have a 48-port unit that's serviced by 3 different ASICs. So port 1 through 16 connects into ASIC number 1, 17 through 32 into ASIC number 2, and then 33 through 48 connect into the third and final ASIC. So they would not be able to create a link aggregation group that cross ports 15, 16, 17, and 18, because that would actually be handled by 2 different forwarding ASICs. So we have no ASIC boundaries on ICXs, but you always need to check what's supported by both of the participating devices whenever you're creating an aggregation group. So all ports in a lag must share the same attributes. So this is software configurable attributes. So they have to be all parts of the same VLAN with the same tagging type assigned to them. All the ports need to be the same speed and duplex. As attractive as it might sound, you can't take a 100 gig link and a 40 gig link and a 10 gig link and a 1 gig link and try to turn that into a 151 gig per second aggregation group. No vendors support that. When you create a lag, you're trying to evenly distribute flows of traffic as closely as possible across the member ports in that aggregation group. So that would not work with differing link speeds on any device. So the QoS priority has to be the same. Any layer 3 configuration has to be the same. Because remember, you're taking the 4 links shown in that diagram and you're making those into one logical port or one logical link. So they have to share the same overall configuration. So in most scenarios, the best practice is to start with a blank slate. So start with a series of 4 ports that have no configuration applied to them, then only after you form the lag, then apply the configuration to that logical lag interface. Now, speaking of the logical lag interface, or the lag port, prior to 8061, we didn't have a logical lag interface on ICX devices. So again, this is an example. If you have a mixed environment with some ICX 6000 and older that can't run firmware versions past 8030, but you also have 7000s that are running 8090 within your environment, then those older ICX devices will have a different command structure. So when you're creating a link aggregation group on the older versions of code, anything 8060 and prior, you need to identify a primary port. Let's say, for example, that primary port, if we look at the diagram above us, the lower of those two devices, it looks like the first participating port in that lag is port 1/1/25. So if we made that our primary port and we want to add this to VLAN 22, then I would go to the prompt for VLAN 22 and I would say tag E1125. And that would apply that VLAN to the entire aggregation group, because that primary port became the configuration container for the aggregation group itself. Same would be true if we were applying a QoS value or if we were applying an ACL. We would go to the 1125 port in order to do that. In the modern versions of our operating system, so anything 8061 and later, you don't have to define a primary port. You no longer have to deploy the lag. It's deployed for you automatically when you add the member ports into the aggregation group, and that creates a logical lag interface. So we'll say we create interface lag 5. So now instead of going to the primary port of the lag to associate your configuration, you do that at the lag 5 prompt. Or if we wanted to add it to VLAN 22, we would go to the port for VLAN 22 and we would say tag lag 5 to have that participate in VLAN number 22. So lag configuration, so you would have already seen this in the ICX 150 course. So you create a lag by giving it a name, telling it is this dynamic, static, or keep alive, and there will be more discussions around keep alive lags in Module 3 of this self-paced course. You then add one or more ports into that VLAN itself. So here they're adding port 9, 10, and 11. So they're creating a 3-port link aggregation group. You can name the ports that are members of a lag. So if you have a port naming convention within your environment, you can either apply that port naming convention to the name of the aggregation group itself, or you can apply that by assigning names to each of the member ports, as we see in the example. So now configuration that would normally be done at a port level is now done at that lag interface instead. So here we see they've gone to the prompt for interface lag 1. That matches the ID of the lag that we created earlier. Now from that prompt, that's where they would be defining this as a point-to-point link for rapid spanning tree, or where they would be turning on root guard or BPDU guard or STP protect. Now you would not turn on all these elements on the same link, because you wouldn't have BPDU guard on a point-to-point link within an environment, or you would not use BPDU guard at the same time you're using STP protect at the edge. Those are kind of mutually exclusive options. But it just shows that commands you would normally run at a port level, you now run at the interface for that lag itself. So you go to that lag logical interface, and that's where you apply those configuration values. So when it comes to load sharing over link aggregation groups, we use an 8-bit hash index to define which link will carry the overall traffic. So now this depends on traffic types as to what fields or values we're going to use to generate this hash output. So on some vendors, they only use the destination MAC address as the determining factor as to which traffic will flow across which links. That would be perfectly fine in a client subnet where a bulk of the traffic is going from the gateway down to the clients, because you have a lot of different destination MAC addresses. But somewhere like a data center, or somewhere where your clients are doing a lot of things like real-time video conferencing, where there's a lot of upload taking place, that becomes very inefficient, because all the traffic going towards the gateway has the same destination MAC, and therefore would be carried across the same link in that aggregation group. So in ICX devices, we actually take multiple values and then break that down into a hash output to assign it to a link. So if your traffic is non-IP traffic, so this would be things like BPDUs. This would be things like, link layer discovery protocol is not, sprayed across those links, but something like fiber channel over Ethernet, or even alternative protocols that you don't see as much anymore, but things like IPS XPX or AppleTalk. So things that are non-IP traffic, we don't have IP addresses and other values to use as part of this hash output. So the only thing we know for sure is going to be in those headers is the source and destination MAC address. So, but instead of some vendors that just use only the destination MAC, we'll use both the source and destination. We will simplify that down to an 8-bit value. So that gives us values between 0 and 255, and that value is assigned to one of the links in the overall aggregation group. So that gives us a much more granular distribution of that traffic across the links in the aggregation group itself. Now, if they are IP packets, which, in most environments, over 95% of your traffic is going to be TCP or UDP based. So this is where most traffic decisions are made. So we'll use the source and destination IP addresses along with the source and destination TCP or UDP ports. So therefore, every individual flow of traffic has the capability to have a different hash output value assigned to it, so it could therefore be assigned to a different link in the overall aggregation group. Well, there's traffic that kind of sits in between those two. So there is IP traffic that doesn't utilize TCP or UDP. They have their own IP protocol types. So things like ICMP or IGMP or OSPF, for example, has their own separate IP protocol number assigned with it. So you don't have TCP or UDP ports to work with. So there again, we'll work with the values we have. So we'll take the source and destination IP addresses along with the source and destination MAC addresses to generate our 8-bit hash output value. Then we have IPv6. So again, most IPv6 traffic, just like IPv4 traffic, would be based around TCP or UDP. So we're going to use those same fields that we had earlier, the source and destination IP addresses. So in this case, it would be IPv6 addresses, along with the source and destination TCP or UDP ports. We also add in a new value that's part of IPv6, which is the flow label. Well, what if it's IPv6, but it's not TCP or UDP? So again, that could be ICMP version 6. That could be OSPF version 3 for IPv6. So those would not utilize TCP or UDP. So here there's a little bit of a mistake in the slides. Let's go ahead and correct that in real time, because it says you would use the source and destination TCP and UDP ports. Well, there's no type of traffic that has both TCP and UDP ports for a flow, number one. And also, we just said this is non-TCP or UDP. So let's get rid of where it says TCP and UDP ports, and let's have that say source and destination IPv6 addresses and the flow label. Now, there are some select vendors that use a similar hashing algorithm to this, that they generate a hash based off of multiple fields in the headers to have granular distribution of the flows of traffic. However, what most of them do is they mask off a bulk of those bits. So what most of those vendors do, for example, if they have a 2-port aggregation group, they look at the first bit of that output only, and they ignore the remaining 7. So they kind of mask off those remaining 7 bits, because that gives you resulting values of either 0 or 1. If you only have 2 ports, you only have 2 possibilities. So you just look at that first bit. If the first bit is a 0, you send it down link 1. If the first bit is a 1, you send it down link 2. So that means that if you had a 4-port lag, like we see shown in the diagram above, then you would apply a value of 0, 0 to the first link, 0, 1 to the second link, 1, 0 to the third link, and 1, 1 to the fourth link. So then they're only looking at the first 2 bits of that overall output. So this is efficient, but only under certain conditions, and it can be problematic when it's implemented that way on many vendors. Because what happens, for example, if you lose link number 4? So if link number 4 gets lost, well, you've got to take that value of 1, 1, and if you're only looking at those first 2 bits, you have to assign that full value to one of those remaining 3 links. So you take that value of 1, 1, you assign that over to the first link in the aggregation group. Now you have twice as many flows of traffic being carried across that first link as you have over the remaining links in the aggregation group. So you may overflow that first link and cause it to drop traffic while there's still available bandwidth on links 2 and 3. This is also why many vendors in their best practices guide talk about creating lags that follow a power of 2 rule. They say your lag should be 2 ports or 4 ports or 8 ports or 16 ports, but no values in between, because they are masking off those hash output values and only using the number of bits that would be appropriate for that given size of aggregation group if it followed a power of 2 rule. Now, we do a little bit more granular distribution of traffic flows on the ICX family. So what we're doing instead is we take the full 8-bit output value. We can we'll look at this as a decimal value just to simplify things from a logical perspective, but it would be, a binary value on the device itself. So if I take the first value that I get from my first flow of traffic, and let's say that hash output value comes out to 197. So I'll assign that value of 197 to link 1 in that aggregation group. If the next output value is, let's say, 14, we'll assign 14 to link 2. We'll say the next output value is 82. I assign that into link 3. So whether we have a 4-port lag where one of those links has failed, or whether we have a 3-port aggregation group, I'll just continue following this overall process. So if the next output that I get is, let's say, let's just say 61. I assign 61 into that first link, and if the next output value is 107, then 107 gets assigned into link 2. So by taking that full hash output value and assigning those to links and keeping those as memory resident tables on the ICX, we're able to achieve a much more even distribution of traffic flows, even when you have lags that are not following a power of 2 rule. And even when you have a lag that is following power of 2, but you've lost one of those links. One of those links is offline in this scenario, but yet we still have an even overall distribution of the flows of traffic that are being carried across that overall device. Now, there is another optional configuration parameter that influences the behavior of load distribution. Now, load distribution, keep in mind, is a unidirectional decision. So I'm just making that decision for the traffic that I'm sending out to the other peer. The other peer has its own algorithm, if that's a third-party device, that is used for the flows of traffic that are being sent towards me. But there are certain scenarios where you may want both directions of a given flow of traffic to be carried across the same link. So let's start this with a supposition. So let me kind of clear off the values that we have up here. And let's say for right now, this starts as an individual port and not a link aggregation group. And when we have that as an individual port, we install kind of a transparent firewall in between these two switches or ICXs. So we've got a firewall that is a stateful firewall that is between those overall devices. So that way, when we've got clients in our environment that are connecting to services in the outside world, we are ensuring that there is no kind of invalid responses coming back. So because that is a stateful firewall, it'll make sure the connection request came from one of our internal devices. But let's say over time, our bandwidth needs have increased, or we needed to add redundancy because these were critical services. So they added a second port, and they made that into an aggregation group. So this has now been turned into 2-port lag. Now, let's say that firewall appliance was not an expandable appliance. They couldn't modify and put in a 4-port NIC that was able to create 2 separate 2-port lags between those devices. So in order to address that, they just installed a second firewall on that second port. Well, if they just installed a second independent firewall on that second port, that's going to create a problem. So say I spun up a server in a public cloud service on the internet, and I send out an initial request to that server. So I'm going to send a SYN message, and that SYN message will say this has a hash output of 82, and we assign 82 to that first link in this aggregation group. So that SYN message crosses through that firewall. It is a stateful firewall, so it makes a note in its records about that TCP connection. It then passes on through and goes out to that cloud-based server out on the internet. Now that cloud-based server is going to respond to that SYN with a SYN ACK. So it sends back a SYN ACK. Now, of course, this is going to have a different hash output value because your sources and destinations are reversed. So the output of that is going to be a different hash output. So we'll say its hash output value is 112. And let's say on that other side, 112 gets assigned to link 2 in that aggregation group. So it's going to send it across the second link, which is going to send it to the other firewall. The other firewall doesn't have any match in its table for that SYN ACK. Like none of my internal users requested this traffic. So it is going to take that response, that SYN ACK, and it's going to send that straight into the garbage can. It's saying, no, none of my users asked for this. I'm going to block that. That's some form of attack taking place. So with 2 links in that aggregation group, you would have roughly a 50-50 chance that your TCP session would end up being carried across that same link and that it would be able to successfully pass through the appropriate firewall to be able to forward that traffic along. So half the time the traffic gets dropped, half the time it works. That is not going to be a desirable customer experience within your environment. So you can implement this load balance symmetric function. You would do this on both of the peering ICXs. So when you run the load balance symmetric function, the first phase of this will be exactly the same. So I receive that SYN message on the lower ICX. I generate that hash output value of 82. I assign that value of 82 to the first link in the aggregation group, and I send that initial packet. But before, all of our forwarding decisions were being made when we were sending traffic into the aggregation group. Now the receiving peer is going to pre-allocate that value. So when that initial packet that was sent, that SYN message went from ICX1 to ICX2, when ICX2 received it, it's going to take a look at all those source destination combinations. So in this case, source destination IP addresses and TCP ports, and it's going to reverse them. So it'll flip around the source and destination IPs, and it will flip around the source and destination TCP ports. By flipping those values to their reverse entries, it makes it look like the response traffic. So it generates a hash output of those flipped entries, which comes up with the value of 112. Since it received this SYN message on link 1 in the aggregation group, it is going to pre-assign that value of 112 to that first link in the aggregation group. So you're now no longer just leaving it up to chance of if that return traffic will be carried across the same link. So now when the response comes from that cloud server, we've already assigned that value of 112 to link 1. Therefore, the traffic crosses down link 1 and is seen by the firewall that already has a matching entry in its table from when the SYN went northbound. Since that has a matching entry, it allows the traffic to flow through, and therefore the SYN ACK is able to reach your client, and they're able to start sending traffic out to that server out on the internet. So load balance symmetric forces that traffic to be used on the same links northbound as they are southbound. Only use this when you have a scenario like we've described above, when you absolutely must have the outbound traffic flow over the exact same link as the inbound traffic due to something like, stateful firewalls that are connected to those links. Now, in most environments where you do a lag with a stateful firewall that sits in the middle, you'll do a lag from the ICX to the firewall and then another lag from the firewall to the peering ICX. So you have a single firewall that is tracking that traffic. Then you would not need the load balance symmetric parameter. But if they were independent devices, now you have to ensure that your traffic is flowing across the same link in both directions, and that would be accomplished by enabling the load balance symmetric function. This does generate a bit more overhead because we're looking at, those hash output values, not only for data we're sending into the lag, but for data we're receiving on the lag. So do not turn on that function unless you need to have the traffic flow on the same link in both directions. Now, another important element when you're dealing with a multi-vendor environment is the timeout configuration for LACP. Now, on ICX devices, we automatically transition from a short timer to a long timer after the aggregation group has formed. So when we just bring a link on that's a member of a dynamic link aggregation group, then we're going to have 1 second timers for sending out the LACP to use. And that's to ensure that that lag forms quickly. But after the lag has formed, you don't need to be as chatty. So it's not required to kind of communicate with that other side as often in most scenarios. So we transition to a long timer automatically. So we go from sending a hello once every second to sending a hello once every 30 seconds. Well, that would be a problem if the other vendor stays on a short timer. On their short timer, they're believing that the dead timer should be set to 3 seconds, 3 times that advertise or hello interval. So all of a sudden you'll see the lag forms, it's healthy for 3 seconds and it breaks. And then it forms again, it's healthy for 3 seconds and it breaks. And it forms again, it's healthy for 3 seconds and it breaks. Now I want you to avoid kind of the common pitfall that takes place in the scenario. So in a lot of environments in the scenario, the administrator automatically decides that, one of these two devices doesn't properly support LACP, which we could argue is correct, but then they make the determination that I have to install a static lag instead. Now, changing this from a dynamic lag to a static lag, yes, it would fix the underlying problem. You would no longer have a lag that is forming and breaking and forming and breaking and forming and breaking. But you're going to lose all the benefits that come with a dynamic link aggregation group. So you're no longer going to be able to recognize a miscabling. You're no longer going to be able to automatically recognize a misconfiguration of this aggregation group. If you do miscable it, either today or 6 months from now when they're doing recabling within the environment, and 3 of your 4 ports connect to one peer switch, but the 4th port connects to the wrong switch, you can create loops. You can create broadcast storms within that environment if that is on a static link aggregation group. So it's highly recommended to keep this, to maintain this as a dynamic LACP-based lag, but simply to go to the configuration prompt for that lag. So here we again run the command lag blue dynamic ID auto or whatever ID you had defined when you initially created the aggregation group, and then run the command LACP timeout short. So this says to keep using short timers. So even though the lag is formed, don't transition from that once per second timer into the once every 30 seconds. Keep that built-in initial rhythm of once per second because that's what the peer expects. So by continuing to send those advertisements once every second, the peer remains happy, it doesn't time out, and the lag is no longer forming, then breaking, then forming, then breaking. Now, another optional configuration parameters with aggregation groups on ICX devices is to set your LACP mode to passive. Let me make something very clear. Do not set a passive LACP mode on an ICX device. There's no reason to set it as passive on an ICX. So then you might bring up the question, well, then why do we have the command if there's no reason to do it? We have the command because it's part of the standard. If we didn't offer the capability, then we would not be adhering to the industry standard itself. But the idea of passive wasn't really created for like switches and routers and infrastructure devices that you're going to have very stringent control over. That was more created for edge devices. So, for example, I might have a server with a 2-port NIC that has a NIC teaming driver that comes along with that. And I could configure that NIC teaming driver in a manner in which it will create a lag if it can, but otherwise it will treat those ports as active-passive failover ports. And that is done by it using a passive LACP mode. So since it has a passive mode, when it brings up the interfaces on that NIC, it listens for LACP to use coming from the network. If it sees those LACP to use from the network, it goes, oh, I can turn this into a lag, so both ports would be actively forwarding traffic. So if it sees an LACP to you, it automatically responds to it. However, if it doesn't see one, it just kind of goes, oh, well, no worries. I've been configured in such a way that I'm passive for LACP. I'm not going to send my own LACP to use. Instead, I'll send all my traffic over link 1, and if link 1 fails, then I'll just kick over and start sending all my traffic out link 2 instead. So that gives them an active passive or just a link redundancy scenario when a lag is not being created by the upstream networking device. But as far as the networking devices, there's not any commands on an ICX that says, make these ports into a lag maybe, or make them into a lag when you feel like it. You don't run your infrastructure as do this when you feel like it. You run your infrastructure very rigidly. It's very much these 2 ports go into a lag together, or these 4 ports go into a lag together. So since there's not kind of that wishy-washy element of saying, well, maybe try a lag and see what happens, since it's just period, this is a lag, there's no value in setting a passive mode on an ICX device. And there is danger in doing it. If you set passive mode and you also set passive mode to the peering device, the lag will never form. So that's the only thing that passive controls, is to not send an LACP to you automatically unless you've received one. It doesn't change any of the other behavior of these 2 devices communicating with each other or creating the lag itself. So having active on both sides is perfectly healthy and is the most common scenario. So yes, we support the option because it's part of the industry standard for LACP, but it's an option you should not be configuring on an infrastructure device like a switch or a router. Now, one optional configuration function, which is unique to static link aggregation groups on ICX devices, is a static lag threshold. This is also referred to as a trunk threshold. So this is an ability to take a static aggregation group, and if it falls below a set number of operational links, just bring the entire lag out of service. So maybe you have another lag that's the same size that exists in your environment, but it is being placed into a blocking or discarding state by something like rapid spanning tree. Rapid spanning tree does not have built-in awareness of aggregation groups. It treats an aggregation group as if it was one single logical link. Just like we talk about, we're taking multiple ports and turning them into a logical link. So all of a sudden, when a link aggregation group that was 4 ports, when it starts losing ports and those start going offline, rapid spanning tree is not aware that that bandwidth is going away. So it doesn't have any built-in mechanisms to be able to fail over to a redundant aggregation group. So here, by setting a trunk threshold value, so here we've got a static lag with 4 ports. So we've got 131, 132, 133, and 134. Now, I would highly recommend do not set a trunk threshold that is the same size as your aggregation group. If you set it the same size as the aggregation group, then even a momentary flap of a port because someone happened to trip over a cable or bump into it when they were working in the data center or the wiring closet, that would bring the entire lag out of service. You don't want that. So always have this at least one link smaller than the maximum size of that aggregation group. So here we've got a trunk threshold of 3. So as long as 4 ports are operational and healthy, everything's left alone. When there are 3 ports operational and healthy, that's still okay because we're still meeting that threshold value. But as soon as we go below 3, as soon as we cross the threshold, now we have only 2 healthy ports. If we had another 4-port lag that was in a discarding state, we would much rather fail our traffic over to that other lag. So we'll automatically bring the entire lag out of service. So this will disable the port members if that number drops below that value. Then when those other ports recover and we once again reach that threshold, that re-enables the aggregation group itself. Which then brings us into the concept of protected ports. So protected ports, this is an alternative to private VLANs. So you can't